Hey guys, it's time for section 3, starting one of my favorite parts of this chapter, which is talking about something called logarithms. And this is where you're going to see a relationship between exponential functions and logarithmic functions. So today we're going to focus on evaluating logarithmic functions, which is also going to include putting things that are logarithmic into exponential form and vice versa. And then in the second video for this section, we will focus on graphing. All right, so the new vocabulary you need to worry about in this section is logarithm and logarithmic function. Most of the rest of our chapter is going to focus very heavily on logarithms. So this is an important section because it's an introduction to what they are and how they work. Okay, so basically, if we want to sum it up, a logarithm is the inverse of an exponential function. So if you look at this graph, the blue graph is an exponential growth graph like we looked at in section 1. This particular one is y equals 2 to the x. Well, if we take the inverse, and remember for the inverse of a function, if you think back to chapter 6, for the inverse of a function, we switch the domain and the range. We switch x and y. So if I switch x and y and write it like this, x equals 2 to the y, this is what the graph looks like. You can see that it's a reflection over the line y equals x, as inverse functions always are. And you can see that the 0.01 becomes the 0.10, the 0.24 becomes the 0.42, and so on. So let's compare this a little bit. Here they show us the two tables of values, and you can see that the domain and the range just switch. When we rewrite our function like this, x equals b to the y, when we write x equals b to the y, that's the inverse of the exponential function, and we solve for y, which looks like this, and we're going to look more at this notation in a second. But basically, when we write it like this, that exponent, that y, is called the logarithm of x. It's what exponent do I need to take this base to get some answer. And the way that we read this notation, so basically, if I want to write x equals b to the y in y equals form, it looks like this. Y equals log base b of x. This is the same as saying b to the y equals x. These two things are synonymous. So take a look again at the function. Notice the exponential function has the x-axis as an asymptote. The logarithmic function has the y-axis as an asymptote, right? And they look like inverses because they're a reflection over y equals x. So basically, the domain of the exponential function is all real numbers, and its range is greater than 0. In the logarithmic function, that's the red one here, the logarithmic function, my domain is x is greater than 0, so I cannot take a logarithm of a negative number, and my range is all real numbers, so it switches. Okay, so this is how we work the notation. It says let b and x be positive numbers, b cannot be 1. A logarithm of x with base b is written like this, log base b of x. And it's defined as the exponent y, so logarithms are exponents. The exponent y that makes this equation true, right? How can I get x by taking b to some exponent? That exponent is called the logarithm. And this is the relationship. This side of the equation is called exponential form, and this side of the equation is called logarithmic form. So they're going to ask us to go back and forth. So log base b of x equals y if and only if b to the y equals x. So if I'm going to apply that to this example, if log base 3 of 27 equals y, then 3 to the y equals 27. It kind of follows a nice circle. And we're just totally basing this on this definition. A logarithm is just another way to express the exponent when y is in the exponent instead of x. And we're going to use this to take something that's in logarithmic form and rewrite it in exponential form. So let's take a look at this example. Log base 3 of 9 equals 2. Since everything here is numbers, this one is going to be pretty logical. Remember we said that log base b of x equals y is the same as b to the y equals x. So in this case, b is 3, x is 9, and y is 2. So 3 squared, using this definition, has to equal 9. So this is logarithmic form. We're writing it in exponential form. And this is very logical, right? It's true. 3 squared is equal to 9. We can see that relationship there. Okay, let's try this one. Log base 10 of 1/100th equals -2. Same process. This is my b, this is my y, so 10 to the -2 equals 1/100. And we can see that that relationship is true. 1/100 is equal to 10 to the -2. Notice that when it's in logarithmic form, what it's equal to is the exponent, right? But then in exponential form, that goes back to the exponential place. Okay, why don't you guys try this one? See if you can write it in exponential form. Okay, exponential form here is 2 cubed equals 8. 2 cubed equals 8. And try this one. Again, changing from logarithmic to exponential form, you should get C, 3 to the -2 exponent equals 1/9. All right, we can also go the other way. We can take something exponential and write it in logarithmic form. It's super important that you pay attention to what you're being asked so you know what format to write it in. So in this case, 5 cubed equals 125. So remember, this is b to the y equals x, and we want to put it into log base b of x equals y. So if I follow that format, right, 5 is b, 3 is y, and x is 125, and remembering that in logarithmic form, the logarithm is always equal to the exponent. So log base 5 of 125 equals 3. You can always check by checking your little circle. 5 cubed equals 125. Yes, that's true, so it makes sense going back and forth. So that would be the logarithmic form. Log base 5 of 125 equals 3. Okay, and this one again, here my b is 27, y is 1/3, and x is 3. So in this case, log base 27 of 3 equals 1/3, because 27 to the 1/3 equals 3. And we will use this relationship in future sections to solve different kinds of equations. Okay, so I want you guys to try. Notice this again is exponential form. We want to put it in logarithmic form. Okay, you should have gotten A. Log base 3 of 81 equals 4. And try this one, 81 to the 1/2 equals 9. In this case, you get D. Remember that whatever the exponent is always what we're equal to when I'm writing it in logarithmic form. So it's log base 81 of 9 equals 1/2. Okay. We're also going to use this definition to help us evaluate logarithmic expressions, meaning to find their value. So when there's variables involved, sometimes we can solve, or evaluate, I should say, with logarithms. So I want to evaluate log base 3 of 243. What does that equal, right? So that's like my variable. I don't know what it equals. How do I find out? So we're going to set it equal to y. You can really set it equal to any variable, but we want to keep it, we don't want to confuse ourselves, so we'll set it equal to y. And then I'm going to take from logarithmic form and I'm going to write it in exponential form, right? So 3 to the y equals 243. And now we're going back to the last section where we have to rewrite things with exactly the same base. So 243 is 3 to the 5th. If 3 to the 5th equals 3 to the y, then 5 has to equal y. And we have evaluated that logarithm. All right, here's one for you guys to try. Log base 10 of 1,000. Try to evaluate that. All right, in this case, you should get 3. Your process is to say, okay, log base 10 of 1,000, what does that equal? I'm going to rewrite it in exponential form. 10 to the y equals 1,000. And then I'm going back to the last section where we solved exponential equations. This is now an exponential equation because my variable is in the exponent. And I'm going to rewrite both sides with the same base. I get 10 to the y equals 10 cubed because 1,000 is 10 cubed. So according to the property of equality of exponents, y has to equal 3. Okay, we're just going to kind of touch on the graphing a little bit in this video, and then we'll do more with the graphing in the next video. So we're just going to talk briefly in this video about the parent function, f of x equals log base b of x. Remember that the asymptote is the f of x, or the y-axis, because this is the inverse of the exponential function. Its domain is all positive real numbers, so the domain is x is greater than 0. I cannot plug a negative number or 0 into my logarithm, and we'll talk a little bit more about why in a minute. The graph is continuous and one-to-one. Its range is all real numbers because it will grow infinitely, even though it grows very slowly. It will grow forever. And the x-intercept, in this case, is 1, 0. And again, this is the parent function before I've applied any transformations or anything like that. So notice that on the left-hand side, this graph is when the base of my logarithm, my b, is greater than 1. So this is the inverse of an exponential growth function. So it's like an exponential growth function flipped over the line y equals x. When I have exponential growth, notice that these 3 points are on my graph, and this is super important for what we're going to do when we graph in the next class. The point 1 over b negative 1, the point 1, 0, that's my x-intercept, and the point b, 1. And remember, my b is coming from the base of my logarithm. What I have on the other side is when my b, the base of my logarithm, is between 0 and 1. So it's a fraction between 0 and 1. This is the inverse of an exponential decay function, right? So imagine a function that was coming down like this. And this is the reflection of that function over the line y equals x, although my graph is not super beautiful. So in this situation, b1 is the point right here. 1, 0 is still my x-intercept. And 1 over b, negative 1, is another point out here. Those 3 points are going to be super important when you are graphing logarithmic functions. Okay? So, oh yeah, I was going to point out to you why we cannot take a logarithm of a negative number, right? So if I have log base 2 of 3, well, let's do one that's a little easier to figure out. Log base 2 of 8 equals 3. That's true because 2 cubed is equal to 8, right? If I go back and forth between the two, logarithmic form and exponential form. But if I try to do log base 2 of negative 8 equals something, right, some exponent, 2 to an exponent cannot give me a negative number. Right? Remember that y is always an exponent. So no matter what exponent I do 2, if I do 2 to the negative 3, 2 to the negative 3 is 1 over 2 cubed, or 1/8. That's still a positive number. So there's no exponent that I can take this 2 to, that I can raise the 2 to that power to get a negative number. It also doesn't work for 0, right? If I have log base 2 of 0 equals what? That means 2 to what exponent gives me 0? Nothing, right? If we think about the exponential function 2 to the x, 2 to the x looks like this. It gets infinitely close to the x-axis. It gets infinitely close to 0, but it never actually touches 0. So I cannot take a logarithm of 0 or of a negative number, and that's super important to remember. That's why my domain is all positive real numbers. X is greater than 0. All right, in the next video, we will practice actually graphing logarithmic functions and transforming them vertically and horizontally. But for now, tomorrow in class, we will be practicing logarithmic and exponential form, and we will be practicing evaluating and the very basics of what a logarithmic function looks like. So I'll see you then.